Okay, so we're going to continue with chapter 13, talking about discrete random variables. We covered a very important one last time, the binomial random variable. How do you know if your situation can be multiplied by a binomial distribution?
Can you repeat it, like experiment?
You have a repeating experiment. What else? Only two kinds of outcomes, right? Success and failure. What's the third criteria? They have to be independent, right? So you have to know this because they're not going to always tell you, oh, this is binomial. Sometimes they're just going to describe the situation. You have to realize that these three things fall into play. So you need to know that. So that was a very important one. Super important, especially for the final, because it's guaranteed to come on. Next, we're going to talk about one that's far less likely, but it's something you should know about anyway. You might encounter it in some of your other classes. It's called the Poisson distribution. So we're not going to spend a lot of time on this, but I think you should just know about it. The Poisson distribution. Poisson. Poisson. Just say it with a French accent. Okay, so it's called a Poisson distribution. It sort of comes from the binomial. It's sort of what a binomial turns into if n is large and p is small. All right, it's a extremely good approximation in that case. However, it's mostly used for this situation. So when do you use a Poisson? So we know when we use a binomial, but when do we use a Poisson? It's when we expect a certain event to occur. The variable is lambda times on average. In a certain interval, usually a time interval. Right, so if you know how often something occurs on average for some given window, could be a time window, usually it's a time window, then you can use a Poisson distribution. And its formula is that x equals the number of occurrences then in the given interval. Then the probability that the event will occur k times is given by this formula. Lambda to the k, e to the minus k, e to the minus lambda. Over k factorial, which we remember what factorial was from last time, right? It's just the product of all integers from 1 up to k, the number. So the average is, as I said, lambda, and we also know the standard deviation. This is the radical of lambda, and the variance equals lambda, which is the square of the standard deviation. let me give you an example. I don't know if I'll actually go through it. We'll need it for the homework though, I think. In a certain college dorm, one can expect So that's an example of a problem. So you could say something like a certain college dorm, one can expect students to pull like 21 pranks per week, right? So if you're the new kid, what is probably that the students turn over a new leaf and they won't pull any pranks today, right? Or what is the probability that they'll pull 2 pranks today, or at least 1 prank today, or less than 4 pranks today, right? So basically we're given an average number of expected things of an event, expected occurrences, right? The event is pulling the prank. We can expect an average of 21 of those per week, right? And then I give you a time window, which is a day, in a given 24-hour period. What is the probability that you expect a certain number of pranks, right? So for here, what would your lambda equal here, do you think? I'm not going to solve it, but I'm just saying. "21 is the number of pranks you will be pulled in a week."
7 divided by 7.
Right. So on average, if you pull 21 pranks per week, that means on average there are 3 pranks per day, right? You just divide that by 7 for each day. Since we're talking about a day, we need to get the average for the day, right? So I would actually use lambda equals 21 over 7 equals 3. And then for here, you would use k equals 0, right? You want 0 pranks today with this lambda in that formula. And that will actually give you the probability. Here, you would want k equals 2. Here, you'd want k is greater than or equal to 1, which means you can do 1 minus the probability that k equals 0. Right? And here, you just have to bite the bullet, do 4 computations. P of 0 plus P of 1 plus P of 2 plus P of 3. Right? So I'm not going to go through it. I just wanted to show you an example. It's a pretty typical kind of distribution to use because a lot of times we know this information. On average, you can expect this to happen this many times, right? So especially anything that happens on some sort of schedule, you'd use this distribution to describe it. So like a bus schedule, you know, on average, you know, 5 buses come every hour, or on average, this geyser explodes this many times per year, and you want to actually use that information to predict, you know, some sort of future behavior, future number of occurrences, right? So if you're like on an island with a volcano, and you know, on average, this volcano erupts like, you know, once every 3 years. What's the probability it's going to erupt this year? You know, you can do that. You can't predict for sure, but if something is established to happen a certain amount of times on average, this is usually a very good approximation for the chances of it happening in the future. So that's sort of what the Poisson distribution is used for. Not super important. You can try that on your own. Maybe we'll look at it later, but it's an important distribution. It's just not that much emphasis is given in our syllabus. That ends chapter 13. We're going to move on to chapter 14. We're going to continue with random variables. But now we're going to look at continuous random variables. So remember what discrete meant. Discrete meant you can only take on certain values, like the integers are discrete, because in any given interval on the number line, an integer can only take on certain values on that number line, and it can't take on others. While a real number can take on any position, right? So that's the difference between continuous and discrete, right? You can continuously take on any position that you'd like, right? Because not everything can be counted. Some things can be measured. You use discrete when you can count something. Like here, I can count the number of pranks, right? I can't say you did 21 and a half pranks today, right? You can't really say that, right? You either made a prank or you didn't. This one you can count, you can only take on certain values. You're counting the number of pranks. You can only take on integer values. But what if you're measuring things like average height? Your height can be anything. There are infinite number of heights you can have. Or the length of something, right? It doesn't have to only take on integer values, it can take on any value in a given integer, right? So for things like that, we have to go to continuous random variables. This sort of complicates things. It's best to use what's called a probability density function. Abbreviated PDF to measure probability. Some of the theory behind before we get into examples. A PDF for a continuous random variable. let me call the PDF f of x. One, your f of x has to be greater than or equal to 0 for all x. 2, the area under f of x on the entire real line must be 1. We want to describe our function in such a way that so basically what we want is we want to be able to describe probability by giving us some sort of function that's always non-negative on the entire real line. And if someone were to ask you, what is the probability of x being between a and b, right? Then you can find the answer by taking the area under this graph. And you can somehow make it so that the area so if you're given an interval, you can somehow use this probability density function to figure out the probability because the area over a certain interval coincides with the probability on that interval. I.e., the probability of A less than or equal to X less than or equal to B is equal to, how do you think we'd measure the area for a continuous random variable? Area under a curve. That's right, the definite integral. Yes, that is correct. Okay, so if f of x is your probability density function, you can actually find the probability of being on this interval between a and b as just the integral between a and b. Yay, we have calculus and probability now. Which means, once you can describe a function that gives the probability density function of some event, you can use integrals to figure out probabilities. And this actually has some consequences. Oh, by the way, it doesn't matter if these are strict or not. Right? Meaning it can be less than or equal to, the probability will be exactly the same. Does it matter? Okay. Because we're considering it as an interval. Right, so some comments here. Really went all out describing this. So I mentioned this before, we never went into detail, but remember when we were doing something like this, and we said if we could draw our histogram so that the width here is 1, and that part gives you the relative frequency, then say you were here at, this is the value A, then the area of this rectangle here was the probability that you would actually attain that value. I actually mentioned that. I didn't go deeply into it. But basically, with this idea, you can sort of go from area to probability quite easily. Because the height, the relative frequency is sort of the probability multiplied by 1. It doesn't make a difference. So if you have rectangles with the width is 1, the height is the probability, then the area of the rectangle coincides with the probability. So the idea is now with continuous guys, you don't want to be confined to just this integral. What if you want to take a piece of this one and a piece of that one? Right? Which discrete random variables can't do, but we want to actually extend what we can do. So it sort of came from that idea. I could generalize that too. It doesn't have to be relative probability, relative frequency. Okay. Another comment is for any constant A, the probability that x equals A is equal to 0. If x is a continuous random variable. Why? Because the probability of x equals A is pretty much the same as just measuring the integral from A to A, f of x dx, which is always 0. You're asking for the integral under a line, basically, right? If you take the integral at a point, you don't actually get an interval, there is no area, right? So this sort of tells you, it's probably counterintuitive, but in the continuous case, this has to be the case, right? So if you're looking at the heights of people and you ask, what's the probability of randomly selecting someone with a height of exactly 5 feet and 0 inches? What are the chances of someone being exactly 5 feet and 0 inches? Pretty much nothing, right? If you measure things carefully enough, it's pretty much going to be impossible to randomly pick something that's continuous and pinpoint an exact point, right? You actually can't do it. Continuous things are a little bit more elusive in that sense. And comment 2 is what suggests there's no difference between less than and less than or equal to as far as you're talking about conditional probability, because if you're at a point specifically, it doesn't really matter, right? It adds nothing to your probability, basically. And if you see strictly greater than and greater than or equal to, again, no difference, because being equal to a value doesn't add anything to your probability. So that's why these greater than or equal to or less than or equal to, it's the same, right? For continuous random variables, not for discrete. Right? So there are a few differences we have to take into account. So the idea behind the continuous random variable is you want to come up with a continuous function that describes your probability in the ways that I described here. It always has to be positive because a probability it always has to be non-negative because probabilities are non-negative. The total area must equal to 1 because the sum of all probabilities has to equal to 1. And we want the area on an interval to be the probability of falling in that interval. Okay? And of course, the area of a specific point is 0. Therefore, the probability of picking an exact value is 0. So be aware of that. I'm moving quickly through some of these because it's not super important for our syllabus, but it's important that you know them nonetheless. And there are some homework problems on them. So. There's something called a uniform distribution. Why is this called a uniform distribution? Well, the idea is the graphs of these are rectangles, right? No matter what your x value is, the probability at that point, at any given point, the chances of something happening is always the same. We call this a uniform distribution. Right? So we have we're looking at the area between some point. What is the probability that you're between A and B? Well, for that to happen, we need to make sure that the height of the graph is 1 over b minus a, right? For the total graph, not specific portion. Value between a and b, the area under the whole graph has to be 1. So if you have a rectangle where the base, the length would be b minus a, then the height has to be 1 over b minus a. So when you take length times width, the area is 1. Right? So the graph would look like basically a rectangle. That's what this is called, a uniform distribution. So over here would be b minus a. This line here would be your f of x. And it's 0 elsewhere, so that you're not getting an area bigger than 1. Running along. It's the next distribution that's the really important one. So we're just going to try to get through this quickly. So if I give you two values, x1 and x2, then all you have to do is find the area between this graph. And then you're done. So that would mean the probability is just x2 minus x1. Length times width. in some ways you can sort of think of this distribution as the continuous analog of the Poisson distribution. If you know that something happens on average in some certain time interval, but it's not a discrete case, then you can use a uniform distribution. So if you're looking at, again, maybe a bus schedule, but you're looking at the times when the buses will arrive. Like you can say, oh, you know, a bus arrives at this stop every 5 minutes. Time is a continuous variable. Time doesn't only take on certain values. So if you're looking at the time, then you'd use a uniform distribution rather than a Poisson. So, like I said, the next one is a really important one. I just want to hurry through this and get through it. Okay. So I mentioned here, distribution is uniform since all outcomes in a range between A and B are equally likely. The probabilities are uniformly distributed. I'm not going to write that down. Here's an example. Let's hurry up and talk about this, then we talk about the normal distribution. Oh my God, so excited. Okay, all right, let's rush through this guy. Okay, how do you think you'd go? The good thing about these ones is that you don't need a calculator. Uniform distributions used to be a typical final question problem on the finals, but in recent years, not so much, but you never know. So they are easy, so if someone throws a curveball and puts one of these guys on the exam, it should be no problem. How do you think we'll start off? So a question, by the way, if they didn't describe it this way, a question that could give rise to something like this is if someone said, you know, between the hours of 3 p.m. and 5 p.m., the bus arrives roughly every half hour, right? Then if you want to measure the probability of the bus arriving in a certain time window, this would be how you do it. Right? It's uniform distribution because probability is distributed evenly. You're measuring time, which is continuous, and so on and so forth. So something like that.
Shouldn't it be 0?
0 where?
The probability?
For A,
Yes.
it'd be 4.
How do you know before?
I mean 1/2, because 4 is between 3 and 5. x, right?
It's 0. Any constant.
Right, probability of any constant is 0. So probability of x equals 4, 0. You're like, what's the probability of the bus arriving exactly at 4 p.m.? 0.
So like all 0?
Yeah, it's almost a trick question. You literally don't have to write anything. It's 0 because the probability of x equals a constant. Okay.
So
C. Yes.
only if it's 3 and 5, that's the x1 and x2. That's the only way it would ever be 1/2, and besides that, it's always 0.
At any specific point, it'll be 0. What about C now? So it's not a specific point. This is an interval. It's outside of the range, right? Basically what is happening here, like if you see something like this, one of the first things I'd probably do is just draw the picture. What does the picture look like? Well, I know it's between 3 and 5, and it has to be a rectangle. What would the height of this rectangle be? Well, they told us it was a half. So you know it's a half. Right? Because the length is 2, the height is a half, length times width is 1, so the area under this graph is 1. So we know it's a probability, it's always non-negative. And so when someone asks me, you know, what's the probability that x equals 4? Basically what they're asking is between 3 and 5, what's the probability that you're exactly on this line 4? Well, it'll be the area under the graph, which is the area under a line, it's nothing, right? Same thing here. What's the probability that you're exactly on the line 3? 0. You can't pinpoint that line. The area under the curve is 0. However, in this case, they asked us, what is the probability that you are between 0 and 1? But the graph is 0 here. So probability that x is between 0 and 1 is also 0. Okay, not so bad so far. Now we're going to look at something a bit non-trivial, but it's still not a problem, really. D. What's the probability that you're between 3.5 less than or equal to x, which is strictly less than 4? So here's our picture. 3, 5. This is a half. Quarter. So
Should be 1/4.
So this is probability, this is x. Right, so we are going to look at the area under the graph from 3.5 to 4. So it means you're going to start at 3.5, you're going to go right up to 4, right? So basically to find the probability, we're just going to look at the area under this graph. So what's the length of the interval? 0.5. It's 4 minus 3.5, which is 0.5. This means probability in between 3.5 less than equal to x less than equal to 4 is just the area of this, which is just going to be 0.5 times the height, which is 0.5. Right? Which is what? 0.25. Basically, this is length times height. Right? It's just a rectangle. Anytime you're finding an area, it's just length times height. So they'll pretty much tell you what interval you're in, and you try to figure out what area that covers. Usually no calculator necessary. You do it in your head. Let's look at E. 3.5, but now I'm strictly less than x, strictly less than 4. That complicates things. How do we do that one? It's going to be the same thing. to do. It doesn't matter if these are strict or not. Right? So that's a trick question. Don't be trying to do stuff again. Okay. So uniforms are sort of nice. We're just finding areas of rectangles. What about the probability that x is between 4 and 6? So this is 3, this is 5. Here's my rectangle. The height is 1/2. Right, so how do I do this one? Is it 0?
What's one side of the ring? Half of it.
So what interval are we looking at?
So 4 or 5.
Six.
We want to start at 4. Where do we want to end?
6.
6. Which means I need to find the area under the graph between 4 and 6. How do I do that?
Just the area between 4 and 5.
It's just going to be the area between 4 and 5, right? I'm just going to break up this area into 2 pieces. There's a piece between 4 and 5, and I can add it to the area between 5 and 6. But the area under 5 and 6 is 0, so overall the area is just the part between 4 and 5. This means the probability of your variable occurring between 4 and 5, 4 and 6, is basically just the probability between 4 and 5, which is length times height. So the chance of that happening is 1/2 length height. So at any point you just draw this picture, right, which they're going to tell you from the function. They're going to give you the interval. And the height has to be such that it's 1 over the length of the major interval, and that will give you a probability distribution. And anytime they ask you a question, you just want to know what is the area under the interval that they're asking me about. That's uniform. Okay, let's get to the fun stuff. Now this is guaranteed to come on the final, and you're guaranteed to see it again at some point. We're first going to talk about the standard normal distribution, and then we are going to generalize this. Why is this important? So why this is important is that by far, most things we care about falls under this distribution. We live in a very complex world, and complex things usually have a normal or approximately normal distribution. Anything with a lot of characteristics or a lot of moving parts, such as human beings, which is what we mostly study. What's the probability of you getting cancer if you smoke 2 packs a day? Right? That's a question about human beings. Human beings are complicated. They actually follow a normal distribution. A lot of things follow a normal distribution. It's a very, very, very ubiquitous distribution to use. And you will see it later when studying statistics. So where does it come from? Here's the function. 1 over the radical of 2 pi e to the minus z squared over 2. It's a very nice one. Yeah, we're going to be integrating that. Okay, so let's go.
Sounds really exciting.
It's called, I am excited. The PDF for this distribution is blah. Normal density. Okay. Why is it the standard? Well, basically, it's the graph of hell, I'm going to go ahead and say it, the perfect bell curve. Perfect bell curve. Perfectly symmetric. Perfect symmetric bell curve. Let me do that. Perfect symmetric bell curve. Right? So basically, if you look at a bell curve, perfectly symmetric. Like, I cannot draw this perfection, but this is my best attempt. Where the mean happens exactly in the middle of the number line. This is where the mean is. And if you go back one standard deviation, or go forward one standard deviation, the standard deviation occurs at the number 1, which is super important, the unit. And on top of that, the total area on the entire real line is equal to 1, right? So this is a bell curve. The mean occurs at the center at 0. The standard deviation is the unit 1. And when you measure the area from negative infinity all the way to positive infinity, the area is exactly 1. So you think of a function, so mathematicians are like, okay, we want to create this function that looks like this, like this perfect thing, let the mean be right in the center, standard deviation is 1, the total area under the graph is 1. What would that be? This function. We're not going to go in how they got that, it's way beyond our scope, but basically this function describes this curve, the perfectly symmetric bell curve where your mean and your standard deviation are very nice numbers. Basically, once we figure out everything about this guy, then everyone else that can be approximated by a normal distribution is just merely like shifting and stretching. And, we can sort of shift things like make the mean something else, make the standard deviation something else, but sort of maintain this curve. We can make it thinner, longer, stretch it. But basically what we do is we figure out how this one works, and then we can figure out any other one. Right? So here, probability equals area under the curve. Right, so here I have this guy. I say, what's the probability that we're between A and B? Well, all I'm going to have to do is find the area under the curve. That's all we have to do. That's our function. No problem. Right? But, and here's what makes this so awesome. It turns out we can't integrate this guy. It has no antiderivative, basically. There is no function we can think of where when we take its derivative, we get this. So here they're like, okay, let's come up with a perfect function. Boom, that's it. Okay, great, let's find the area. Oops. Doesn't have an antiderivative. not in general. It turns out, though, we can find the definite integral, though. Right, so it doesn't have any antiderivative in terms of elementary functions. There are no functions that you've seen in all of elementary calculus, Calc 1, 2, and 3. There is no function you can come up with that when you differentiate it, you get e to the minus x squared over 2, or e to the minus x squared, for that matter. But we can approximate the definite integral on this guy within any desired degree of accuracy. How? Well, basically through numerical integration, right? So basically you go through and you do something like set up a Riemann sum, right? You get the summation and you can approximate the summation to any number of decimal places you want, basically, right? All you do is just you take your Riemann sums and you keep evaluating the series until it stops at a certain number of decimal places you like. If you've been doing the Excel homework, you've actually used this principle before, where you did that whole thing where it computed all the values in the table, and they're asking, how do you know you have 2 decimal place accuracy? Well, you just do the number of subintervals so that the first 2 decimal places stay constant after a while. And you say, okay, I just need that many subintervals. So basically that's what we do. We look at this graph, and we start cutting it into subintervals. And we measure the areas of these little rectangles. And we just take enough subintervals to get enough decimal places that we want through like Excel or something like that. I wouldn't want to particularly do this by hand, but people have done it by hand. I mean, they were using this before they had powerful computers. Okay. So yeah, doesn't have an antiderivative in general, but we can use Riemann sum, Simpson's rule, trapezoid rule. Did you guys do that in 205?
Random sum?
Huh?
The random sum?
Like Simpson's rule, trapezoid rule? They do it in 201. Okay, well, never mind. You can use Riemann sums like a right-hand rule or midpoint rule or whatever, right? And you can do it so that you get the definite integral for any desired accuracy. Okay. So that's how we overcome that problem. We're like, yes, we have this perfect function. No, we can't take the integral. Don't worry, we have a fix, because we're never going to ask in general, right? We're always going to, what is the probability between here and here? What's the probability we're in this interval? A question will always be phrased like that. Or you should be able to phrase it like that. So once we can find the definite integral, we are good. Okay, so well, every time you want to find a probability, you don't want to go through a Riemann sum. So what they did, they were very nice. We then put these values in the table for easy reference. It's in the appendix. However, last time I actually gave you this table. So now you actually know what it means if you didn't know what it meant before. Do I have a copy? I told you guys to bring it today because we were going to use it today. You guys have it with those tables out. Give me your top. Okay. So this is basically the table, right? So that's the symmetric bell curve. And what these values in the table actually give you is the shaded area, right? So I actually mentioned that. And There are different ways to measure the area. Some people measure the area starting from the center, but our particular table and the one in your book measures it from negative infinity. So the table gives the area to the left of some point. i.e., the probability from negative infinity up to some point A equals area in the table. You have that perfectly symmetric bell curve, the mean going through the center. And then there's some point A here where if I look from that point and everything to the left, what is the area going all the way back down to negative infinity? All I have to do is just look it up in that table and it will tell me. So notation. For shorthand, we will sometimes write the following. The probability of negative infinity, so I can use this, A is called phi of A. Right? So it's just a fancy thing for the area up to A, right? We call it phi of A. So let me show you how to use the table. So the first thing you want to do when you see one of these random tables, some textbooks measure it differently, is you look at the picture. They always have an accompanying picture where they tell you what is being measured. So they'll shade whatever is there being measured. Then what's going to happen is they put a value called Z here, and usually the first two decimal places, first two digits of Z is here. The second decimal place is here. And the area is here. So if you're looking for an area, you're looking at it in the table. So for example, if I wanted to find phi of, let's say 1.25, basically, this means, remember 0 is at the center, 1.25 is here. Basically, I want to find the area up to 1.25. Basically, what I'm going to do is I'm going to go to the table. I'm going to look here to find the 1.2. And then they're going to, how do they have it listed here? Here they have 0.00, 0.01. And at some point, you're going to hit a 0.05. So this will give you the 1.25, right? So you sort of match this up, right? Your row and column are going to come together to give you the 1.25. And whatever number you find in that position is going to be your area. So in this particular case, if you're looking at this table, the positive numbers are over here. So you look for 1.2, and then you move over until you're under the 5. So this will be 1.25. So what is that?
1.8944.
So it would be 0.8944. Make sure you can actually find that on the table on your own. So the first two digits are here. The third digit is over here. Right? You sort of just match it up on the table. Right? And basically what that is if you actually looked at the integral from negative infinity to 1.25 of 1 over radical 2 pi e to the minus z squared over 2 dz, that would be approximately this. Right? But they did the Riemann sums and everything for you, and they just made it correct to 4 decimal places, and they said that's the value. So, let's do some more examples before. I want you guys to try looking this up. It's going to be a very important skill for doing these problems. Based on the given. I forgot what the table is called in the book. It's called cumulative standard normal probabilities. Compute. I'm going to want you to find these for me. The probability that your z is less than 0.1. I also want you to figure out what is the probability that your z is greater than 2. What is the probability that your z is between 0 but less than 1.5? Greater than or equal to 0 but less than 1.5. I'd also like you to find the probability, A, B, C, D, that your absolute value of z is less than 1. C, D, E. All that your absolute value of z is less than 2. Probably absolute value of z is less than 3. That I did on purpose. You're going to see where that comes from. You're going to see what happens there. Lastly, I want you to find the point z0 such that the probability of z greater than z0 is equal to 0.05. So I'll give you guys a few minutes to knock out some of those, and then we'll go through it together. So this is just sort of how to look things up mechanically. We're going to be applying this to making applications here soon. So the idea is if there's a standard normal, there will be, of course, non-standard normals, right? And those are the ones that are really important, right? What if your mean is not 0 and your standard deviation is not 1, but you know it's sort of normally distributed? How do you figure out the probabilities then? We're going to be doing that. But being able to do these is going to be very important. Very, very, very important. Also, what I'd like you to do is, with your answer, draw a little picture of the area that you're finding. That helps. And sort of shade the area that you want to go after, and that will help you to figure out the values that you should be looking at. our intermission, I'm going to do my happy feet dance. Okay, go. Okay, we're ready? Okay, let's do this. Don't have much time, I want to get through all of these. We'll probably stop here and pick up next time after we get through this. Okay, what's the answer? Huh? 0.5398. So if you look at the picture, what are you actually looking for? Well, I know the 0 is here, 0.1 is a little over. So basically what I'm looking for is the area under the graph from negative infinity up to 0.1. I want to be less than 0.1. Right? So what I'm going to do is I'm going to go into the table. I'm going to look for 0.1. And of course, the second is going to be 0, 0. And it's going to be that number. So that's on this side. I look up 0.1. And the second digit after the decimal point is a 0, right? So that is 0.5398. Yeah, and there's nothing else to do. What about this one, part B? What area are we trying to find? This is 0, that's 2. So the area we want is where? So all of this, right?
No.
Oh, right, over here. But the table gives us the area on the left. How do we do that?
1 minus.
1 minus, right. So we know the whole thing, the area, equals 1. The table is going to give us this. Phi of 2 is going to give us this. So if you want the rest, all we have to do is just take 1, subtract this guy, and we're left with that guy. So this is basically, it's sort of like we're using a complement probability. This is just 1 minus the probability that said is less than 2. Testing less than or equal to, but like I said, it's continuous, it doesn't really matter. So it's just going to be 1 minus. Now you're going to look up 2 in this table, which is going to be on the right side again. You go down to 2.0, comma 0, 2.00, and that will be 0.9772. So you take 1 minus 0.9772, and what did you get?
0.0228.
0.228. So that's the probability that you're actually greater than 2. What about this one? So here I am between 0 and 1.5. So basically I want this area.
Probability is less than 1.5 minus 1 minus the probability of 0.
Minus what?
1 minus the probability of 0 is greater than 0. Or just less than 0. Less than 0. Less than 0, right.
You actually don't need this.
Yeah. I put 0.9332 of 1.5, right? I might have done that.
Okay.
Yeah, so 0.9332 minus the probably like 0.5. Should get that area.
Yeah, so the idea is in the table it tells you the area to the left. So what you can do is you can find the area up to this point, right? So you can look up phi of 1.5, right? So you go to your table, you look up 1.5, the next one is 0. So that's going to be, in this case, 0.9332. And then you can look up to 0, right? Like what's phi of 0? Well, that's just 0.5, right? Because 0 is right in the middle, the area is 1, the area up to 0 then will be a half. And so what you can do is, you actually want the area between these two. So all you do is you take this guy minus that guy, and it leaves you with what you want, right? So the probability of 0 is in z less than 1.5 is just going to be equal to the area under 1.5 minus the area up to 0, which is just going to be 0.9332 minus 0.5, which is 0.4332. Okay. And this idea sort of works in general. If you want z between A and B, then you just sort of find the area up to B minus the area up to A. Right? Just by looking at the picture, you can see, oh, if I take this minus that, I'm left with this. Right? So you can sort of use the graph as a guide. Let's look at D. Less than 1. What does that mean? How do we do that? What does it mean for z to be less than 1 in absolute values?
Just less than one.
Less than 1 in absolute values doesn't mean less than 1.
We add the 2. Minus
What does it mean? Absolute value x less than a means what? Huh? No. It means you can break it up into 2 parts. Remember? This is minus x is less than that. That's what it means. So basically saying this is the same as saying I want the probability that z is between minus 1 and 1. Which I can say, well, this is just phi of 1 minus phi of minus 1. Or I could actually there's another way to do it, but in this case, never mind. For this table, this is probably the best way to do it. There are other tables that start at the halfway mark, and I could tell you another way to do it, but whatever. Basically, there are times you can use symmetry. This is what we want to find. But remember, there's perfect symmetry here. So the area between 0 and 1 is actually the same as the area between minus 1. For our table, we don't even have to think about that. It's just easier to just look up this value minus that value. So we would look up 1. Some tables, like I said, measure from the halfway mark, and to get that, you could have just doubled this value, and you would have found it that way. But our table goes from negative infinity all the way up, so it's probably better to do it this way. So I would look up phi of 1, which is 0.8413, minus phi of negative 1, which the negatives are on this side, for negative 1.1587. And what's that?
Point 6826.
0.686826. Huh?
Are these the standard deviations, the 68, 95, 90?
Yeah, well, way to steal the thunder. I was going to build up to that whole thing. I was going to like, oh, look at the last 3 you did. Anyone notice anything? Thanks a lot, Lily. Jeez.
Sorry.
Like, you couldn't even wait until I like did the other 2, could you? Yeah, this is where the 68, 90, the bell curve rule comes from. And you thought so, we just made it up. No, it's actually... Less than 2 means we want the probability that you're between minus 2 and 2, which means it's probability of being between 2 minus the probability of between minus 2, which is the probability of being at 2 is 0.9772 minus the probability of being at minus 2, 0.0228. And this is, what's that? entropy of 3 is all the way down here, that's 9987. Minus 3 is 0.3821. And what's that? What's this number?
0.95.
0.95 what?
44.
4. And this one is
0013.
Yeah, show 0013 then.
for
Not
not
negative 3.
for negative 3.
Instead of 0.3821,
0.0013. Yes. I thought that would be. Because negative 3 is way down there. 0.0013. Yeah, I was testing that. Okay, so what's that?
0.9974.
Okay. Does anyone notice a pattern?
No.
No. Yeah. Man, I have to tell you guys everything. This is where the 68, 95, 99.7 rules come from. You see how that works out? You think we pull it out of a hat? No, we were looking at the antiderivative of e to the minus z squared over 2. That's where it came from. Okay, the last one. Let's see who's thinking. I want to find the point where this is true. Find z0, so the probability of z is greater than z0 is equal to 0.05. In statistics, that's actually, when you go further in statistics, that's going to be an important number when you're looking at the 95% confidence interval and things like that. Which is in chapter 15, we won't really do it. Okay, ideas.
1.6.
1.65.
So basically, what we can do here is we draw a picture and we sort of draw what we want to accomplish, right? So we want some point where the area over here is area equals 0.05. We want to find the point z0 that makes this happen. Right? That's basically what we're looking for. But if the area over here is 0.05, what does the area over here have to be? This means the area on this side, you want it to be 0.95, because the area has to be 1. So basically all I have to do is figure out what value actually gives me an area of 0.95 in this table. So where do we look for that? How do we figure that out? Here's 0.95. Where do we look? So basically we're going to look in the table, right? And we're going to look for 0.9 here and then 0.05. Is that correct?
No. 0.95 inside.
Yeah.
Right.
So tricky.
So remember, I'm just telling you. I'm sure you like mistakes I've seen, all right? I'm not just trying to be mean. I've seen students like look things up this way, right? Remember I described the table, right? On the far left column and the top row, that gives you the z value, not the area. Area is found inside the table, right? So you have to remember in the table, this is the z value. This is the second decimal place of the z value. Areas are in the table. So if I want to figure out where is the area 0.95, I have to find 0.95 somewhere in this table. Right? So basically I'm going to look for that. And then I backtrack to find the z value that gives me that. So I'm going to look for 0.95, right, the closest approximation.
1.6 and 0.05.
Okay, so you see it here. At 1.64, I have 0.9495. And at 1.65, 5, I have 0.9505. They're pretty much exactly, like the value we want exactly in the middle. You can even average them, but you probably don't even have to. So basically, we look up, you'd realize that when you have 1.6, if you have 1.64, or if you look up 0.04, that's going to give you 0.9495. You look up 0.05. That's going to give you 0.9505. 0.95 is smack dab in the middle. You can average these two if you want and put like 0.45 as the last two decimal places, but you usually don't have to get that crazy. So we'll continue over here. That would roughly be the value, which is going to be your Z value when you're looking up the 95% confidence interval. So that's basically the idea between that. So now we were just looking up values, and that's how it's done. Later, next class, we're going to actually apply this. Any questions? I haven't asked if there are any questions like this whole class. I just assumed you all knew what I was talking about. You're all smart kids. So allow me to troll my friend here for a second. Look at this graph. Okay, all right, you can cut it off.